Hello everyone, myself Dr. NCH Ramgopal, working as Associate Professor in Mathematics, Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. I welcome you all to the today's session on analysis of variance. Let us recall the previous session. In the last session, we have discussed the test concerning goodness of fit test and fitting a theoretical distribution. How to fit a theoretical distribution to the given frequency distribution. For example, fitting a binomial distribution, fitting a Poisson distribution, etc. And then we have discussed the procedure of goodness of fit test. In goodness of fit test, we test whether the given data follows a theoretical distribution or not. And also we have discussed the conditions for validity of chi-square test and problems on goodness of fit test. Coming to today's presentation, today I would like to introduce the concept ANOVA, analysis of variance. So, introduction to ANOVA, one-way classification, ANOVA test and then problems on ANOVA. Now, coming to the introduction to ANOVA, ANOVA is developed by R.A. Fisher in 1920 and it is one of the powerful tools of statistical analysis. If the number of samples is more than 2, then Z-test or T-test cannot be used. In such cases, we apply the F-test, and also it is used to test whether the difference between the means of 3 or more populations is significant or not. That means, if the data is given regarding 3 populations or more than 3 populations and 3 samples or more than 3 samples, then to test whether there is any significant difference between the means of populations, we apply this ANOVA test, and it is widely used in natural, social and physical sciences. ANOVA split up variance into its various components. Now, there are 2 types of ANOVAs. One is one-way ANOVA and two-way ANOVA. So, it is classified into 2 types. One is one-way classification and two-way classification. In one-way classification, one dependent variable and one independent variable. In two-way calculations, we will have 2 dependent and more than 2 independent also. And here, we will discuss the one-way classification of ANOVA. And ANOVA measures 2 sources of variations in the data and compares their relative sizes. So, from the given data, it considers the information regarding 2 sources of variation and then compare their relative sizes also. Variation there are 2 things we calculate in ANOVA: variation between groups and variation within groups. So, in variation between groups, for each data value, we look at the difference between its group mean and the overall mean. So, we check the difference between the group mean and overall mean also. That comes under between groups. Similarly, variation within groups, for each data value, we look at the difference between the value and mean of its group, the actual value and the mean of whole group. So, variation within groups and variation between groups, we use these 2 values to test whether 3 or more than means are equal or not, and that test is called ANOVA test. And ANOVA, the actual definition we can say as a statistical tool for detecting differences in the group means when there is a parametric dependent variable and 1 or more independent variables. Now, specifically, we are interested in determining whether differences exist between population means or not. So, in particular, we can say ANOVA can be applied when the problem is related to 3 or more than 3 populations and to test whether the difference between the population means, we apply this ANOVA. And the steps involved in ANOVA, the observations are classified according to the one factor, that comes under one-way classification. So, in one-way classification, the observations are classified according to one factor. So, in step 1, we calculate the total capital T of all observations in K samples. So, there will be K populations and K samples, and the data will be given the observations of these K samples 1, 2, 3 and so on, K samples. Then let us calculate the total T, sigma x1 plus sigma x2 plus so on sigma xn. So, this first one indicates the first one sigma x1 indicates the observations corresponding to sample 1, and second one indicates the observations corresponding to sample 2, and so on, the last xk corresponding to sample k. Step 1, we calculate the total capital T, and in step 2, find the correction factor using the formula T square by n. So, the total which we have obtained in step 1, square the value of the T divided by n, where n is the total number of observations. So, the correction factor is denoted by Cf given by T square by n. So, in ANOVA, first we calculate the total of all observations given in the samples, then find the correction factor using the formula T square by n. In step 3, now we calculate the sum of squares of all observations in k samples, sum of squares of all observations. For example, you see here sigma x1 square, sigma x2 square, sigma xk square. So, sum of the squares of all observations. First we square all the given observations and then we consider the total for sample 1, that is sigma x1 square. Consider sample 2, square all the values or the observations given and add all those square values. So, that is sigma x2 square. Like this we calculate for all k values and again find the total of all these squares, sum of the squares, and subtract from this T square by n. We subtract this value T square by n, which is the correction factor just now we have calculated in step 2. So, let us subtract that from sum of all observations in k samples and subtract Cf from it, which is called the sum of squares of deviations, sum of squares of deviations, and let us denote it by SST. Now, in step 4, find the sum of squares of deviations between the samples. As just now we have discussed, there are two types, between the samples and within the samples. So, between the samples, first we calculate the sum of squares of deviations, that is calculated using the formula SSB equal to, this is sum of the squares of first sample observations divided by the size of the sample, sigma x2 square second sample, sum of the squares of second sample observations divided by n2 and so on. From this subtract the correction factor T square by n. So, this gives SSB, sum of squares of deviations between the samples. In step 5, we calculate sum of squares of deviations within the sample. So, let us denote it by SSW. This SSW can be calculated using the formula SST minus SSB. Just now we have calculated SST in step 3 and SSB in step 4. So, SST minus SSB, that gives the sum of the squares of deviations within the sample. After finding all this, we can construct this table, which is called ANOVA table, source of variation. So, from which source we are calculating, that means whether we are calculating between or within, and second, sum of the squares. So, since source of variation is having two things, between and within. So, corresponding to this between, sum of the squares, so it is denoted by SSB, and for SSB the degrees of freedom mu1 is given by k minus 1, where k is the number of observations given in the problem. So, how many observations are given, that is the value of k, and k minus 1 is the degrees of freedom denoted by mu1. And MSB, mean squares, then we calculate the mean squares corresponding to between the samples. So, MSB is SSD by k minus 1. Then within SSW, sum of the squares within the samples is denoted by SSW, and degrees of freedom is given by capital N minus k, capital N total number of observations, and this is the size of the sample, and MSW is SSW by k minus 1. And finally, the test statistic in ANOVA test is F is given by MSB by MSW. So, here we calculate MSB, mean squares between and mean squares within. Ratio of these two mean squares is the calculated value of F, which is the test statistic in ANOVA test. So, in ANOVA one-way classification, we test the null hypothesis H0, that there is no significant difference between the means, between the given means, and the problem will be of either 3 or more than 3 populations. So, there will be 3 or more than 3 populations, that means we consider either 3 means or more than 3. In that cases, to test whether there is any difference between more than, greater than or equal to 3 population means, we apply ANOVA test. And our null hypothesis or the statement which is to be tested is there is no significant difference between the population means. And we test this null hypothesis against the alternative hypothesis H1 that there is some significant difference between the given means. And the critical reason is given by since there is one and only one type of alternative hypothesis, there will be one condition only. Always the same, if our calculated value is greater than the tabular value, simply we can reject the null hypothesis. So, if calculated value is less than tabular value, we accept null hypothesis. If calculated value of f is greater than that of tabular value, simply we reject the null hypothesis. Now, let us discuss one example on ANOVA test. The following data gives the yields of 12 plots of land in 3 samples. Each of the plots under 3 varieties of fertilizers A, B and C. So, there are 3 different samples, sample A, sample B, sample C. Overall observations 12 values, 12 plots. In sample A under 3 varieties of fertilizers. So, fertilizer A that comes under sample 1, fertilizer B sample 2, fertilizer C sample 3. So, there are 3 samples, that means 3 populations, 3 samples. So, it comes under test of hypothesis concerning difference between more than or equal to 3 means. So, in that case we apply the ANOVA test. And here you can see there are 3 columns and 4 rows for these values observations, 4 into 3 12, total 12 observations. Now, the question is there any significant difference at 5% level of significance in the average yields of lands under 3 varieties of fertilizers? So, after using 3 different varieties of fertilizers, is there any difference between the average yields, that means mean yield of the land? That we need to check. Now, here the test is as follows, having 6 different steps: null hypothesis, the actual statement which is to be tested, alternative hypothesis, any hypothesis other than null hypothesis, that is called alternative, level of significance will be given in the value given in the problem, which is the probability of committing type 1 error, and critical region in which the region in which we reject the null hypothesis, that is the critical region. We write the condition here, calculation part, the formula, and finally we take the decision by comparing calculated value and tabular value. This is the actual test procedure of testing of hypothesis. Now, in ANOVA test, the null hypothesis, what is the actual problem? Is there any significant difference in the average yields of lands? So, the null hypothesis always will be taken in the form of there is no difference in the average or mean yield times of the land. There is no difference between the 3 varieties in the average yields of lands, that we need to check. So, we consider the null hypothesis as there is no difference, and against the alternative hypothesis, yes, there is some significant difference between the means. Since there are 3 samples are given, we cannot apply, there will be 3 means, so we cannot apply either Z test or T test. That is why here we apply this analysis of variance test. Now, coming to level of significance, it is clearly given alpha value is 5%, which is 0.05, the level of significance alpha is 0.05, and the critical region reject the null hypothesis if the calculated value is greater than the tabular value. And calculation, just now we have discussed the procedure and the calculations involved in ANOVA test. So, the F calculated value is given by MSB by MSW, mean squares between the samples divided by mean squares within the samples. So, to find these two values, first we need to construct a table, the given x1 values, x2 values, x3 values, and square them, x1 square, x2 square and x3 square, and find the totals. So, this is the total column, total of these column values. So, total of x1 is 92, total of x2 is 72, x3 is 100 and so on. So, let us construct this table. Then first we calculate the total. Total is the sum of all observations. So, x1 corresponding to sample 1, x2 corresponding to sample 2 and this x3 corresponding to sample 3. Let us find all the totals. Then the CF value, correction factor, t square by n value. So, this is given by 5808. Using those values we can calculate this. So, this one is also sigma x1 92 plus 72 plus 100. So, the total of these three values and square it divided by n gives 5808. And now the sum of the squares between the samples is given by this formula. Subtract correction factor from the sum of the squares of deviations. So, which results as 104 and the total SST sum of the squares is 176 and we have the formula to find within the sample. Sum of the squares within the sample is SST minus SSB. So, 176 minus 104 which results as 72. So, first we need to calculate all these values which are to be used in the calculated value of f. Now, let us construct the table. If we construct this table, this gives the calculated value. So, source of variation is between the samples, within the samples, sum of the squares. Just now we have calculated SSB 104, SSW 72, SST 176 and degrees of freedom mu1 is k minus 1 equal to 2 because k is here, there are 3 samples are given. So, nu equal to 3 minus 1, 2 degrees of freedom. Overall observations, so nu 2 equal to n minus k, that is also calculated and MSB formula, use the formula. So, we will get 52 MSB and MSW is 8. So, mean square between the samples is 52 and mean square within the sample is 8. So, therefore, the calculated value of f is MSB by MSW. So, 52 by 8 which results as 60.5. So, this is the calculated value. So, f calculated and to take the decision, the tabular value using alpha for given 5% level of significance, the alpha value is 4.2. For alpha equal to 5% level of significance, the f alpha, this for nu1, nu2 degrees of freedom is 4.2. So, f 0.05 for nu1 is 2, nu2 is 9, the answer is 4.2. This is the tabular value and this is the calculated value. Since the calculated value is greater than the tabular value, you can see here we have to reject the null hypothesis if calculated value is greater than the tabular value. So, here we got the same calculated value is greater than tabular value, therefore, reject H naught. What is the H naught considered? There is no difference in the average yields. So, we are rejecting this H naught. What does it mean? We have to accept the alternative hypothesis that there is some significant difference between the 3 means of different yields or fertilizers A, B, C. Hence, using this F test, we can test whether all the population means are same or not. That we can take the final decision by comparing the tabular value and calculated value. Since the calculated value is more than the tabular value, we reject the null hypothesis that there is no difference between the 3 different brands of fertilizers. So, that is that we cannot accept. Hence, we have to accept the alternative hypothesis. So, accept the alternative hypothesis that there is some significant significant difference between the means, population means. That is the final decision. Now, coming to the summary of today's session. Today, we have discussed a particular test called ANOVA, Analysis of Variance, which has many applications in present industry and day-to-day life problems also. And now, we have introduced the concept and then the different types of ANOVA test, one-way and two-way classifications. In that, we have discussed about one-way classification. Under this one-way classification, how to test whether all the population means are same or not. That procedure, step by step procedure is discussed, and also through an example, the ANOVA test is clearly discussed. Thank you very much.